In this video, we'll be discussing some of the various definitions that have been used for acids and bases. Historically, there have been three primary definitions for acids and bases. The first was proposed by savant Arrhenius, and his definition is known as the Arrhenius acid-base definition. Arrhenius said that for acids, those are compounds that release a proton, an H+ ion. Examples of this include HCl, HF, HBr, NH4+, the ammonium ion, H2SO4, and acetic acid, CH3COOH. Examples of Arrhenius bases, well, those are ones that release a hydroxide ion, so they would include things like sodium hydroxide and potassium hydroxide. Bronsted and Lowrey later expanded upon the definition first proposed by Arrhenius. They kept the definition of acid the same, those that release a proton. Under their definition, they call them proton donors. So the list of acids is the exact same as what was proposed by Arrhenius. HCl, HF, HBr, things like that are still considered acids under the Bronsted-Lowrey acid-base definition. What Bronsted and Lowrey did was they expanded on the definition of bases. So instead of just things that release hydroxide ions, bases are things that react similar to Arrhenius bases. Those are things that can accept a proton, and it's anything that can combine with a proton, such as NH3, NaOH, or the acetate ion, as well as many other things. Lewis of the Lewis acid and Lewis of the Lewis dot structure also proposed a much more expansive definition of acids and bases. Under the Lewis definition, acids are electron acceptors. So anything that was previously considered an acid under either the Bronsted-Lowrey or the Arrhenius definition are still Lewis acids. But because we now have anything that can accept an electron, not just a proton ion or an H+ ion, things like BH3 and silver ions are now considered acids. For bases, the Lewis definition are electron donors, and this actually means that they are the exact same as what used to be, or what Bronsted and Lowrey called bases. Anything that can accept a proton, it does that by donating electrons. And so the sum of the molecules, or the list of molecules that were Bronsted-Lowrey bases, are also Lewis bases. We can actually clarify this by sort of a Venn-like diagram, taking a look at how the definition of our various acids and bases changed between the various definitions. So our first definition is the Arrhenius definition. So if we look here, Arrhenius. Our Arrhenius definition is this inner circle for both the acid and the base. So Arrhenius has things like proton donors, HCl, CH3COOH, H2SO4. The key is that for Arrhenius acid, it's something that can donate a proton. For bases, under the Arrhenius definition, they have to donate or give off hydroxide ions. So things like NaOH, sodium hydroxide, CaOH2, calcium hydroxide, KOH, potassium hydroxide. These are all examples of Arrhenius bases. For our Bronsted Bronsted-Lowrey definition, the acids stay the same. Right? But our bases now expand to be a much larger set. So everything here in this inner circle that used to be Arrhenius acids are still Bronsted acids. But the bases have expanded to include not just the ones that were the Arrhenius, so they include all the ones that used to be Arrhenius bases, but now they have things like the acetate ion, CH3, COO minus. This can accept a hydrogen to give back the acetic acid. We can also have things like ammonia, or ammonia can accept a hydrogen. Anything that has the ability to accept a hydrogen or a proton is now under the definition of a base. So it includes everything that used to be an Arrhenius base, as well as a new series of molecules that don't have hydroxide ions with them, but they react with water to act the same way as what would be categorized as Arrhenius bases. The next definition is the Lewis. So our Lewis acids are now this larger category. And the Lewis bases are the exact same as the Bronsted were. So Lewis acids are anything that can accept electrons. So like BH3, Ag silver plus, copper, Cu2 plus, anything that has an unfilled shell or unfilled orbital can accept electrons from a Bronsted or a Lewis base. Now, what happens when the hydrogen ion or a proton is donated using the Bronsted-Lowrey definition? And it's the Bronsted-Lowrey definition that we're primarily going to be using in general chemistry. Right? The Lewis definition is what will get used to some extent in certain upper-level organic classes, but primarily when most chemists talk acid-base, they generally are referring to the Bronsted-Lowrey definition. Right? So the Bronsted-Lowrey definition again is proton donors are acids, proton acceptors are bases. So what happens when you take an acid and you put it into water? Well, the H plus ions that are produced by acids are very reactive, and they don't really exist in water in the H plus form. So H plus ions, we call them protons. When something that donates protons is put into water, it immediately forms what we call hydronium ions. So that is these H3O plus ions. So the reaction is the proton comes off of your acid and immediately reacts with the nearest water that it comes into contact with to give you a hydronium ion. There are also minor amounts of H plus with multiple water molecules around them, but primarily what we're just going to be considering is the hydronium ion itself. So H3O plus is the form that you will find protons in an aqueous environment. So that could be H plus reacts with water. So this water here has these two lone pair of electrons, right? So by the Lewis definition, you would donate these electrons to form a bond with hydrogen to give you the hydronium ion. By the Bronsted-Lowrey definition, instead of focusing on the electrons, we focus on the proton. So for the Bronsted-Lowrey definition, instead what we have is the proton comes in and gets bound to the proton acceptor. So the water acts as our proton acceptor, our base, and the H plus is our acid. Now, often what you'll see is chemical equations for acids breaking apart. Sometimes you'll see the H plus written as an aqueous solution. It's really actually the hydronium ion, the H3O plus, but a lot of times you'll see H plus being written as sort of a shorthand notation so that we don't have to write out the entire H3O plus. So when you're looking at a balanced chemical equation, you should think of this as being the same thing as H3O plus. It's just a shorthand form for representing the hydronium ion in an aqueous solution. So Bronsted-Lowrey, it's going to be our working definition for the rest of the semester in terms of acids and bases. The acid is a proton donor, the base is a proton acceptor. The base structure must contain an atom with an unshared pair of electrons, right? So an example of this would be, well, water was one that we already saw. We could also look at ammonia. So if we draw out ammonia using the Lewis dot structure, you'll see that it has two lone pair, right? Those two lone pair are what are responsible for accepting the electron. So for a Bronsted-Lowrey acid-base reaction, the acid molecule donates an H plus to the base molecule. So you have your hydrogen attached to some molecule. This whole thing here is your acid. The base has to have a lone pair of electrons that are capable of accepting the proton. So the hydrogen gets transferred to the base. You then have what was your acid and is now your conjugate base. We'll get into that in just a second. This is left behind, and the hydrogen has been transferred to your base. This is now called a conjugate acid. The definition for an acid, Bronsted acids are, again, proton donors. Any material that has a hydrogen potentially could be a Bronsted-Lowrey acid. However, because of the relative strength of bonds that hold hydrogen atoms on, some hydrogens are going to be easier to transfer than others. Commonly, a carbon-hydrogen bond is very strong and will virtually never act as an acid. Things like OH bonds, oxygen bound to a hydrogen, these can be much weaker, and often the hydrogen is able to come off and act, and that group can act as a proton donor. So things like hydrochloric acid can dissolve in water. When it does so, the hydrochloric acid is considered an acid because HCl transfers a proton to water, forming H3O plus, our hydronium ion. Water acts as the base by accepting the proton. So you have your acid here, HCl, donates this proton to water, which acts as the base, yielding the chloride ion and a hydronium ion. The easiest way to be able to tell that something acted as an acid and something else acted as a base is compare your reactant side to your product side. In this case, the reactants, you have some component here that has one more hydrogen on the reactant side than it does on the base. In this case, your chlorine here on the reactant side has a hydrogen. On the product side, it does not. For the base, you'll be able to identify it because on the reactant side, it has one less hydrogen than that molecule does on the product side. So over here, it's H2O, and on the product side, it's H3O plus, right? One more hydrogen than it had before, and so that tells you that this is the base. For Bronsted-Lowrey bases, those are things that are proton acceptors. Any material that has atoms with a lone pair can potentially be a Bronsted-Lowrey base. Now, some of those lone pairs are more accessible than others, so some bases will be better at accepting a transferred hydrogen than others will be. When ammonia dissolves in water, the NH3, the ammonia molecule, acts as a base because the ammonia will accept a hydrogen from water, forming the hydroxide ion OH-. In this case, water acts as an acid, donating the hydrogen. So if we compare the reactants and the products again, ammonia here has 3 hydrogens, NH3, and over here on the product side, it has 4, NH4+. So we can tell that this nitrogen picked up an extra proton, and so that tells us that this part here, this, on the reactant side, it was acting as a base. Water, here, H2O, gave up a proton to become the hydroxide ion, OH-. So essentially, this oxygen used to be bound to 2 hydrogens, and now it's bound to 1. Because it went down in the number of hydrogens that it has, we know that it acted as the acid. Now, from the 2 examples we just looked at, you might have noticed that water in the first acted as a base, and in the second acted as an acid. Substances that do this we will call amphoteric. So an amphoteric substance is one that can act either as an acid or as a base, depending on what it's being reacted with. And that's because they have both the ability to transfer a hydrogen atom and they have a lone pair that they can use to accept a hydrogen atom or a proton. So water acts as a base when it's reacting with hydrochloric acid, as we have here. We have the HCl donates a proton to the water, and we get the hydronium ion and the chloride ion. So here, water is acting as the base. It's accepting a proton to become the hydronium ion, and in our second reaction, we have ammonia reacting with water to give ammonium and the hydroxide ion. So in this case, your water acts as an acid, right? It donates one of its protons to the ammonia, giving you ammonium, which now has 4 hydrogens. And the result is you get the hydroxide ion. So these are the key thing from this are the 3 definitions of your acids and bases. You have the Arrhenius definition, in which acids are proton donors, bases are hydroxide donors. This was then expanded by Bronsted-Lowrey, where acids are proton donors and bases are proton acceptors. And then the Lewis definition, which is much more expansive, is acids are electron acceptors and bases are electron donors. For our class, we are primarily going to be interested in the Bronsted-Lowrey definition. So when we're talking acids and bases, what you should really be doing is focusing on where the hydrogens are moving. If something is losing a hydrogen atom in a balanced chemical equation, right, it ends up donating that proton to the other substance. And so the one that is doing the donating or losing the hydrogen is the acid. The one that gains the hydrogen or the proton acts as the base. There are a handful of substances, water, for example, that can act as either an acid or a base, depending on what they are reacting with, and those are called amphoteric substances.